In section 6, we want to find the sum of an infinite number of terms in a geometric series. This is finishing off State Standard 22 and finding the sum of the infinite geometric series that we have in blue there. So that's our objective, find sums of infinite geometric series, but this can only work for certain kinds of common ratios. And that's the case where the absolute value of that common ratio is less than 1. So let's talk about that for a minute, because the concept of how can you add an infinite number of numbers together and get a sum that's not infinity is an interesting question. So if an infinite series approaches some limits as a number of terms n becomes very large, that limit is defined to be the sum of the series. In that case, if an infinite series has a sum, it's said to be convergent. And this is somewhat like the idea when we graphed hyperbolas, that the line was approaching the asymptote, never crossing, never touching, never getting parallel to it. So our theorem says that if we have an infinite geometric series and it's convergent, it has a sum if and only if its common ratio meets this condition. And that condition is that the absolute value of that common ratio must be less than 1. So let's look at a particular geometric series. 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus ... infinite geometric series. As we look at this, as the number of terms gets larger, each term itself gets large. So eventually one of these terms itself is going to be approaching infinity. And in that case, then the sum of that series is also going to approach infinity and not be convergent. And we can show that this theorem that we just talked about illustrate that this particular series does not have a sum. If we look at that in more detail, the common ratio is 2. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64. So the common ratio of the above geometric series is 2. If we take the absolute value of 2, we don't get a number less than 1. So in that particular situation, we say the series is divergent as opposed to convergent. What if we look at something like this? What if we had the reciprocals of each of those terms? 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16, etc., plus 1 over 512, plus eventually 1 over 2 to the n power. In this particular case, if we found the sum just the first term, we would get 1/2. If we added the first two terms together, a half plus a fourth, we would get 3/4. If we added the first three terms together, we would get a half plus a fourth plus an eighth, or 7/8. If we added the sum of the first four terms together, we would get a half plus a fourth plus an eighth plus a 16th, or 15/16. And if we took the sum of the first 10 terms, a half plus a fourth plus an eighth plus a 16th plus, etc., 1,024, we would get 1,023 over 1,024. And it appears that the more terms we add to our partial sums above, the closer and closer and closer this number is approaching 1. So a half, 3/4, 7/8, 15/16, and we jump from the sum of the first 4 to the sum of the first 10. We get 1,023 over 1,024, getting closer and closer and closer to 1. So if our infinite series is convergent, the absolute value of that common ratio is less than 1, we can find the sum by using the following formula. Deceptively simple, so it should be easy to memorize. The sum. Notice there's no subscript here, because we're adding an infinite number of terms together. The sum is equal to the first term divided by 1 minus the common ratio. So let's check and see if the following has a sum or not. 1 minus a half plus a fourth minus an eighth plus 1/16 plus, etc., etc., etc. What's our common ratio? Well, that turns out to be -1/2. 1 times -1/2 is -1/2. -1/2 times -1/2 is +1/4. 1/4 times -1/2 is -1/8. -1/8 times -1/2 is +1/16. And that common ratio, the absolute value of -1/2, is less than 1. That is true. So yes, we say that it has a sum. It is convergent. Let's try to calculate it. Using the formula, the sum of the infinite number of terms of a geometric sequence is defined as the first term divided by 1 minus the common ratio. First term here is 1, and the common ratio is -1/2. Simplifying that, when you're subtracting a negative, that's the same as adding a positive. 1 plus a half is 3 halves. 1 divided by 3 halves. Remember, we can't divide by a fraction, so instead we multiply by its reciprocal. 1 times 2/3 is 2/3. So yes, this series has a sum, and it is 2/3. Let's look at another example. We've got 1 plus 5 plus 25 plus 125 plus ... And again, our formula today only works for infinite, if it does work. Here the common ratio is 5 though. 1 times 5 is 5, 5 times 5 is 25, 25 times 5 is 125. The absolute value of 5 is not less than 1. That's false. So this series does not have a sum. This is a series where as we get further out there, one of these terms way out there is going to be really close to infinity itself, so its sum will be. How about the next one? 1 plus negative 1 plus positive 1 plus negative 1 plus etc., etc., etc. Well, the common ratio here is negative 1. And the absolute value of negative 1 is 1, not is less than 1. That's false. So this series does not have a sum. I know you're tempted to say that, but think about it. If you took a sum of an even number of terms, you would get 0. If you took the sum of an odd number of terms, you would get 1. And that's vacillating too much to go from 0 to 1. It is not approaching a limit. It's jumping back and forth between two values. So again, the absolute value of negative 1 less than 1 is false. Therefore, it does not have a sum. We can't use that formula. How about the next infinite geometric series? 5 plus 5 halves plus 5 fourths plus 5 eighths plus, and that pattern goes on forever. Our common ratio is 1/2. 5 times a half is 5 halves. 5 halves times a half is 5 fourths. 5 fourths times a half is 5 eighths. The absolute value of 1 less than 1 is true. So now we can say the sum of the infinite number of terms is equal to the first term over 1 minus the common ratio. First term is 5. Common ratio is 1/2. So 1 minus a half is a half. 5 divided by a half is the same as 5 times the reciprocal of a half, or 2. And 5 times 2 is 10. So the sum of the infinite number of terms here in this infinite geometric series is 10. Well, that's our look at finding the sum of the infinite geometric series.